In the figure, we have a loop of wire, rectangular loop. It consists of 10 turns, so there's 10 coils there. It lies in a horizontal plane, and it's parallel to uniform horizontal magnetic field. So the magnetic field points to the right. A little bit hard to see in the picture, so I'll just trace over some of those arrows. There's our magnetic field in the plane of the loop. Our loop has a current of 2 amps, and the loop is free to rotate about a non-magnetic axle through the center. So we've got our line down the middle, and it can rotate about that point. A 50-gram mass hangs from one edge of the loop. What magnetic field strength will prevent the loop from rotating about the axle? So what's happening here is we've got our center line. It can rotate about this center line. Got a mass hanging off one end. So there's a force that pulls down on our loop, and that's a force due to gravity. Because this force acts at a distance from a pivot, then we get a torque on the loop. And we know that to have no rotation at all, we're going to need our net torque to be 0. So let's jot down a list of what we know. N equals 10, current equals 2 amps. The mass hanging off is 50 grams or 0.05 kilograms. And the distance at which that mass is hanging off, or the distance at which that force is applied, is half the length of the loop. We're given that one side length is 5 centimeters. That's given in the picture. So from the pivot at the center point to where the force is applied, where the mass is hanging off, is half of 5 centimeters, or 0.025 meters. Okay, it's probably best to work in meters so that we don't get confused about units as we go along. Okay, I made a little jumble of what I was writing there. Okay, I think that's more clear now. All right, so in order for it not to rotate, the net torque is equal to 0. The two kinds of torque we can have on it are the torque due to that hanging mass, I'll call that tau m, plus the torque due to the magnetic field. And that's going to be equal to 0. If those two torques are equal, we know they've got to be in opposite directions, and they've got to have equal magnitudes. So the magnitude of the torque due to the hanging mass is equal to the magnitude of the torque due to the magnetic field. They have to be in opposite directions, and they have to have equal magnitudes. That's the only way to get them to cancel. So let's think about each one of those two torques. So the torque due to the hanging mass, the magnitude of the torque due to the hanging mass, is equal to R cross F, where F is the force due to gravity on that hanging mass. So that's the magnitude of R times the magnitude of F times the sine of the angle between R and F. The distance at which it's applied was 2.5 centimeters, 0.025 meters. The force F is the weight pulling down on it, so that's the mass, 0.05 kilograms, times G, 9.81 meters per second squared, times the sine of the angle between them, that's 90 degrees. We can do that in our calculator. We should get 0.0123 newtons times meters. Okay, that's due to the hanging mass. What about due to the magnetic field? Magnitude of torque due to the magnetic field is the magnitude of the magnetic moment crossed with the magnetic field. So it's the magnitude of mu times the magnitude of B times the sine of the angle between them. Magnitude of mu is the number of turns times current times the area. Magnitude of B is B. We're trying to find what B is. Sine of the angle between them is 90 degrees. So our magnetic moment, you make a circle with your fingers that represent your current, and your stuck out thumb represents your magnetic moment. We don't know the direction of current here. We have two possibilities. The current could flow this way around the loop. That would give a mu that pointed up, or it could flow the opposite way around the loop. And that would give a magnetic moment that pointed down. In either case, the magnetic moment would be perpendicular to the magnetic field. So we'll fill in N is 10, our current is 2 amps, our area is the length times the width, 10 centimeters times 5 centimeters, and then I'll squeeze in my B. So the magnitude of that magnetic torque is 0.10 amp times meters squared times B. Okay, let's put these things together in the equation above. 0.0123 newtons times meters equals 0.10 amp meters squared times B. We can solve for B, and what we get for the strength of that magnetic field is 0.123 Teslas. Okay, we did discuss that we didn't know the direction of current. Could we figure it out? That's kind of an interesting question. So let's think in terms of forces. If we look on our loop, and if the gravitational force points down, in order to get this loop not to rotate, there must be a countering force that points up. That would be the magnetic force. Let's draw that in the picture. So the magnetic force would have to point up. Well, what is the direction of I? So FB has to be up. Our magnetic field is to the right. So we can apply our right-hand rule. We know that FB, that's our middle finger, is IL cross B. So I and L, those are your thumb, and B is your index finger. So your index finger has to point to the right. So we're looking at the right-hand part of the loop. Your index finger has to point to the right. You're going to rotate your hand and your arm so that your thumb points, or your middle finger points up. You should see that your thumb points towards you. So on the right-hand part of the loop, that current is coming towards you. So that means the direction of the current around the loop has got to be this way. So I is as shown. So even though the problem didn't ask for it, we were able to figure out the direction of the current. In the setup for our problem, we have two things which are carrying current. We have a wire that has a current flowing out of the page, so the wire is perpendicular to the page. We have a loop that's also perpendicular to the page. In our loop, you can imagine a roll of masking tape if you wish. The current goes away from you on the top, that's what the X shows, and it comes towards you on the bottom, that's what the dot shows. And we want to find the magnitude of the torque on the current loop in the figure. So let's write down our equation for torque equals mu cross B. Mu is the magnetic moment of the loop. So let's see what the magnetic moment is equal to. Mu is equal to the current in the loop times the area of the loop. Our area is a vector and our magnetic moment is a vector. So the area has a magnitude of pi r squared. What about the direction? Well, what you do is you use your right-hand rule. You make a circle with your fingers. Where on the top of your loop, your fingers going away from you, and on the bottom, they come towards you. When you make that circle with your fingers, you should see that your thumb, your stuck-out thumb, points to the left. That's the direction of your mu vector. I'm going to put in my coordinate system x, y, and z, so we see that mu points to the left or the negative I direction. So there's our mu minus IL. IL means I of the loop. Why don't we put that in our picture? Times pi times r squared times I hat, where r is the radius of the loop. I think I'll put an L on there for radius of the loop as well. Sometimes in problems you get a little bit too many L's going on here. So 2 millimeters is the diameter of the loop. The radius of the loop equals 1 millimeter. Get a lot of information in our picture here. Okay, that's our mu dealt with. If we wish, we could go ahead and fill in our numbers right away. I don't think I'll do that just yet. We also need to figure out our B. So what is B? Well, first off, we have to ask what makes the magnetic field in which the loop is sitting. The thing that makes that field is the wire, so it comes from the wire. We know that magnetic fields around a current carrying wire makes big circles, so we can draw that. We'll draw a circle that has the wire at the center, and then the perimeter of the circle will cut through the loop. To get the orientation of the loop, you make a circle with your fingers and you stick out your thumb. Your thumb should point in the direction of the current in the wire, so your thumb should be pointing straight towards you, and then your curled fingers should be pointing in a counterclockwise direction. That shows the magnetic field everywhere on that circle. We care about the magnetic field right at the loop itself. It's going to be a tangent to the circle, so it's going to be pointing straight up. So it points up rather than down because your fingers at that point point upwards. They don't point downwards. Okay, so our magnetic field vector then is mu naught times I of the wire. That's 2 amps. We can label that in our picture. I of the wire divided by 2 pi r, where r is your distance from your wire to your loop. And the direction for that is in the positive y direction. Okay, now all we need to do to get our torque is put in our mu, put in our b, and evaluate our answer. So torque is equal to equal to mu, which is minus I times L times pi r L squared, I hat crossed with mu naught I of the wire, divided by 2 pi r j hat. Minus I L pi r L squared, we can bring all our constants to the front, mu naught I w, divided by 2 pi r I cross j. Now we have a list in which we know all of these numbers. I of the loop is 0.20 amps. Pi is pi. Radius of the loop is 1 millimeter, or 1 times 10 to the minus 3 meters. And what else do we have? Mu naught is our constant. That's 4 pi times 10 to the minus 7. I of the wire equals 2 amps. R stands for the distance between the wire and the loop. That's given as 2 centimeters, 0.20 meters. Put all that through the calculator, and what we get is minus 1.26 times 10 to the minus 11 with units of newtons times meters. Torque, of course, is a direction, is a vector, so it has a direction, and the direction of I cross J is k hat. We should think about what does that mean practically in terms of which way will it rotate. Why don't we spill over onto the next slide to talk about that. So we were asked for the magnitude of the torque. We found the entire vector. The magnitude of torque would be 1.26 times 10 to the minus 4 newtons times meters. Now that we have the torque vector though, let's think what that means about the rotation. We can definitely find the rotation of that loop. So I'll just sketch my loop down here again. So there's my loop. The current goes away on the top and comes towards us on the bottom. To find the direction of rotation, your right-hand rule for torque says that you point your thumb in the direction of torque. Our torque is in the negative k hat direction, so that's into the page away from us. So torque equals thumb. If you take your right-hand rule, you point your thumb away from you, you should see that your fingers curl around in a circle in a clockwise orientation. So your curled fingers come around this way. That shows the rotation. You could also think about the direction of the forces. So we know that the magnetic field points up. We found that on the previous slide. So if you do IL cross B on the top of the page, on the top of the loop, the magnetic force on the top of the loop would point to the right. IL cross B on the bottom of the loop, your magnetic force points to the left. So that supports the fact that the rotation would be in a counterclockwise orientation. Okay, that's the first part all sorted out with a little bit extra. And next, what is the loop's equilibrium orientation? So what that means is how do we set the loop so that it won't rotate? Well, if we want it not to rotate, we want the torque to be equal to 0. To get the torque equal to 0, we'd have to have mu cross B equal to 0. That happens where mu and B are either parallel or anti-parallel. If the mu and B are parallel or anti-parallel, the loop is going to be horizontal. If the loop is horizontal, so let's say it comes away from us there and towards us there, in this case the magnetic moment would be down, and torque equals mu cross B equals 0. And if it were the other direction, then mu would point up. Torque equals mu cross B equals 0. So in either of those orientations, so there's B in both orientations. In both of these cases, the torque goes to 0 because that's what happens when mu and B are along the same direction.